We've seen before how atoms can combine and join together to make molecules. So say, for example, pretty straightforward molecule will be HCl, hydrogen and chlorine. This here are two atoms to make a molecule. But the question arises then is, what decides the shapes of different molecules? How do we determine what the shape of a molecule will be? So the question, I suppose the answer really depends a lot on how many valence electrons an atom has. So you should know what that means at this stage. Valence electrons is the number of electrons in the outside shell. Let's take a molecule. We won't give them actual elements. We'll just use a general formula. Let's take an example of the general formula, AX2. AX2. So this is one atom of A with two atoms of X. The first thing you need to be able to do when you're working out the shape is figure out which of these two atoms is the central atom. The central atom is going to be the one that you have less of. So in this case, we've only got one A. That's going to be the central atom surrounded by two X's. So obviously, the one that there's less of is going to be surrounded by the others. So AX2 is this. A is the central atom. The next thing that's important is to work out how many valence electrons A has, the central atom. So the number of valence electrons, of course, we can get that from the group. So let's say, for example, that AX2 is a molecule and the A is in group 2. So you look it up on the periodic table and you find out that this element is in group 2 of the periodic table. That means that it's got two valence electrons. Let's draw them. One here. Okay, and we'll say one here, two with them. So when it bonds here, it's going to form a pair of electrons, a bond with X, like this. Okay, so here's X, and here's the other one, X. So there's the two X's, and here are the bonds, which are the shared pair of electrons between them. So is this correct or not, if we were looking at the shape? And the answer is, it's not correct, okay? One thing I want to point out before we look at the shape here is that A would be a funny case here, because A is surrounded by only 4 electrons. And we know that when bonding happens, atoms are supposed to get a full stable octet, 8 electrons. Because A is in group 2, it kind of breaks the octet rule. It doesn't have any more unpaired electrons. It doesn't have any more unpaired valence electrons to make 2 more bonds, so it can get to 8. So in this case, 4 surrounding A has to be the best it can get. This is as stable as it can be. Right, that was a little sidetrack, sorry. Back to the shape. Is this correct for the shape? The answer is it's not. And the reason why is that remember what each of these lines are. This line here is a pair of electrons. Electrons have a negative charge. This line here is a pair of electrons. Electrons have a negative charge. Here are two negatively charged areas which want to spread out, repel each other, so they can be as far away as possible from each other. They want to minimize that repulsive force that they're feeling. And they will do this by spreading out as far as possible from each other. So this is not as far apart as possible. What would be as far apart as possible is if they were directly opposite each other. So that's not correct. This would be correct for it. As soon as I can get it, it would look like this. So the two valence electrons would be opposite each other and they would be attached to the X's like this, as far apart as possible. Here is a model of that, where the gray one is the central atom, A, and the two white ones, these are the side atoms that surround it. These are the two X's. And you'll notice that they are fully opposite each other. If we were to think about what the bond angle is here, what's the angle between the two bonds? So this angle here, you will recognize that these are in a straight line to each other. So the bond angle here, we say, is 180 degrees. This here is called the bond angle, and it's important. Each molecule, we're going to look at the bond angle. Okay, so the bond angle is 180 degrees, and the name of this shape, again, this is also important, it's linear. Okay, so that's the first thing. So how do we work out the shape? The first electrons. Then work out the number of bond pairs. In this case, it can only form 2 bonds. So each of these is a bond pair. So this thing has 2 bond pairs, and it's got no other unpaired electrons. That's all it's got, 2 bond pairs. So the shape in that case is linear, and the bond angle is 180 degrees. There's lots of molecules that are like this. Let's look at a different example now. Say we have a general formula, AX3 this time. And we'll say that A is in group 3. Group 3. I'm going to pause the video, write down how many valence electrons it has, do that here. Okay, so A has 3 valence electrons if it's in group 3. We'll draw it here. Here's A. Put the 3 valence electrons around it. Spread them out equally. That's as far out as they can spread, like that. Okay, so we've got 3 valence electrons, and there's 3 X's attached. So each of these is attached to an X, like that. So each of these, because they're involved in bonding, this is a bond pair of electrons. Each of this is called a bond pair of electrons. Again, this shouldn't be brand new for us. We've done this before. This is a bond pair of electrons. So we've got 3 valence electrons, and they're all involved in 3 bond pairs. There are no unpaired electrons. There are 0 lone pairs. Okay, we've got no lone pairs. In this case, this molecule looks like this. So here is the A, and here are the 3 X's. And if I hold it here, you should be able to see that it lies flat on my hand. I hope you can see that. It lies flat. It's in one plane. If we would put a piece of paper on top, it would lie perfectly flat on it. It's all one plane. There's not one of them other. They're all flat. The name of this shape is, we call it a trigonal, coming from the idea that this is a circle divided into triangles. See that? Divided into 3 triangles. Trigonal, and because it's flat, we say it's planar. Trigonal planar is the name of this shape. The bond angle, like we said, was a circle divided into 3 equal triangles. So a circle is 360 degrees, total circle. Divided into 3, the bond angle here is 120 degrees. So 120 degrees bond angle. So this is the case when we have the general formula AX3 and A is in group 3. I'm going to stop at this point and show you some examples of real molecules that have this. So here we need A to be in group 2 elements. So an example of this might be beryllium. And we need group 2 to form single covalent bonds, so pairs of electrons with 2 other atoms. So things that would do this would be chlorine. So this could be BeCl2, it might be BeH2, it might be BeF2, that kind of thing. All of those would be examples. This one here, A has to be a group 3 element. So the one we're mostly interested in is boron. So this might be boron trifluoride, boron trichloride, and boron trihydride. Okay, all of those will be examples of this here, AX3. Next one, let's have a look at another one. Let's say we've got a general formula, AX4, where A is a group 4 element. Group 4 elements include carbon, silicon. So we're going to focus on carbon because carbon's a very common element in a lot of molecules. Say it's a group 4 element. Let's draw it here, group 4. That means it's got 4 valence electrons. 4 valence electrons. If we draw them, we'll spread them apart equally, like that. Spread them apart equally. And it's attached to 4 X's. So each of the X's must be on one of these electrons. So we've got X here, X here, X here, and X here. So that means that all 4 valence electrons are involved in bond pairs. So we've got 4 bond pairs. Notice that there's nothing left over on the A that's unbonded. So 0 lone pairs. Right. So this is AX4. Now, what is the bond angle? This is a little bit tricky because this here is 2D, this page. So to you, this might look like that this is a 90-degree bond angle, which makes sense. It's like a square divided up into 4 pieces. Okay, it makes sense. They look like right angles if you're into your maths. Well, remember that molecules don't exist just on flat pages. They exist in 3D, so they can be spherical. The dimension, they have 3 dimensions, which means that the shape of the molecule is really like this. It's 3D. I'm going to spin it around so you can see that these different atoms go in different directions. So technically, even though sometimes you will see it drawn like this here, this technically isn't that correct. If we were to say, okay, here is my molecule, and if I was to say, here's the central atom, the black one, and I was to put it flat against my hand. So here's my hand. I'm trying to show you that the black one and the 2 white ones that are touching my hand are in one plane. Very hard to do this, sorry. One plane. They're flat against my hand. They won't stay there, sorry. They're flat against my hand. Very hard to see. But at this point, there is one atom coming towards you, which is this one, sticking out away from my hand, pointing your direction. And there's another one coming towards my face. These are not in the same plane as the 3 atoms that are touching my hand. So there's 3 atoms touching my hand, one goes towards you and one goes towards me. So they're actually going in different directions. So technically a better way of drawing this is like this. A in the middle, and there are 2 that are in the same plane, which we show with these solid lines like this. And here they are, there's AX and AX. But the other 2 go in different directions. And scientists often use, or chemists often use, these wedged lines to show this here shows an atom coming towards you, and this atom shows this broken line shows an atom going away from you. So technically now we're not just talking about flat 90 degrees. The angle is quite different now. It's spread out in 3D space. So the angle on this here, so oops, sorry, where are we? This angle here is not 90 degrees. That is not correct. It is 109.5 degrees. That's how the 4 bonds can equally repel each other out into 3D space and get as far apart as possible from each other. So we've got 4 bond pairs, like we saw over here, 4 bond pairs. So they're all the same as each other. They're just bond pairs of electrons, and they're equally repelling each other out. And the furthest apart they can get is 109.5 degrees. That's an important number. So the bond angle here is 109.5, and the shape is called a tetrahedral. Tetrahedral shape. So when you've got a central atom surrounded by 4 bond pairs of electrons, 4 bonded atoms around it, we have a tetrahedral shape. This is group 4. This is carbon. Really common, really important. Let's take another case here. We're going to have to go back over here now. We're going to take another AX3. I'll go back over here. There's another case where we can have AX3. But this time, the central atom A is not in group 3, but it's actually in group 5. Central atom is in group 5. Example, nitrogen. Nitrogen is in group 5. So let's draw nitrogen attached to 3 X's. Or we're not going to say nitrogen, sorry, remember we're just using A. So A is the central atom, and there are 3 X's around it. Here they are. So we're chemically bonded to 3 X atoms, whatever those are, chlorines, hydrogen, something like that. There they are. So we say each of these, remember, is called a bond pair. So each of these is a bond pair. We've got 3 bond pairs. Actually, sorry, never worked out the number of valence electrons. If it's in group 5, that means it's got 5 valence electrons. So we need to make sure we draw 5 valence electrons. So we've got 3 bond pairs where that each of these was the A's electron. This one, and this one. Well, that's only 3 valence electrons I've drawn. There's a total of 6 that I've shown here so far, 6 around A. So A has a share of 6 at the moment. But remember, it's supposed to have 5 valence electrons. So where's the other 2? Well, the other 2 are up here. They just stay belonging to the A. They don't get shared at all. And this is what we call a lone pair of electrons. So 3 bond pairs, 1 lone pair. Well, this is kind of like a tetrahedral. It's got 4 pairs of electrons around it, just like the tetrahedral had. Notice the tetrahedral had 4 pairs of electrons, but they were all bond pairs. So here are the 4 pairs, 1, 2, 3, 4, but they're all bond pairs. This one has 1, 2, 3, and 4, but this time we've got 3 bond pairs, 1 lone pair. And that does make a difference to the bond angle and to the shape. The reason for that is there's this thing called valence shell electron pair repulsion theory, VSEPR theory. Valence shell, so outer shell, electron pair, we're talking about bond pairs or lone pairs, repulsion theory, which shows or which states, this is a theory which gives us the idea that lone pairs repel other pairs more than bond pairs do. So lone pairs repel more than bond pairs. More than bond pairs. So they will push other pairs further away. So the strongest type of repulsion in Vesper theory versus the weakest, the strongest type is if we have 2 lone pairs, LP, LP. Those will repel each other the most, lone pair, lone pair. The next strongest repulsion is a lone pair against the bond pair. And finally, the weakest is 2 bond pairs. So bond pairs will repel each other the least. Lone pairs repel bond pairs more. Lone pairs repel lone pairs even more than that. So the effect of the lone pair here is instead of it being 109.5 like it is up here when we've got 4 electron pairs, the bond angle here between the bonds here and here is reduced because the lone pair is pushing them down. It's skewing the bond a little bit. It looks like this, by the way, in a model. Okay, so here is a model where this is a central atom, the blue one, and we've got 3 white atoms surrounding it. And then this thing up here is supposed to represent the lone pair. So lone pair up on top, and it pushes down the 3 other atoms. So they're not flat anymore. If I put this on my hand, you'll notice that it stands up. There's a space underneath the blue atom. It stands up. So remember, here was the trigonal planar. It was flat. This one is not the same. And that's because this lone pair on top pushes down the bond pairs, pushes them down and stops them from being flat like this one. So the lone pair skews the angle, if you like. So lone pairs repel more than bond pairs. So we can just show that by saying, okay, well, these push down on the bond pairs. Sorry, I don't want that to all correct. Apologies about that. Just get that right. There we go. So lone pairs push down on the bond pairs, repel more, and that changes the bond angle. So the bond angle here, remember what a tetrahedral was? It was 109.5. Well, a lone pair makes a 2.5 degree difference on that. So 109.5, take away 2.5, the bond angle here for the lone pair, with the lone pair is 107. So the bond angle for this molecule is 107 degrees. And the name of this shape, it's called a pyramidal shape. Pyramidal. So note, they love to ask questions about this because this is 2 molecules that can have the same general formula, AX3, but different shapes. So you need to be able to clearly explain the difference between the shapes and why. Okay, examples of this molecule would be something with a group 5 element in it. So something like nitrogen, NH3, or phosphorus, PH3. Those would be molecules that would be very commonly pyramidal shaped because of the lone pair on the nitrogen. Nitrogens and phosphorus always have a lone pair because they're in group 5. That's the difference, and that's how you work it out. The last case, we'll have to go back to the beginning, is we can have another case where we've got a molecule that has a general formula AX2 again. So AX2. But this time, instead of being in group 2, like it was up here, A is in group 6. Group 6. So group 6 means it's got 6 valence electrons. And if we draw the group, the middle atom A, here it is, and 6 valence electrons, but it's bonded to 2 X's like this. So it's got a bond pair with an X here, and it's got a bond pair with an X here. So here I've only shown 2 valence electrons of the A. I need to have 6 valence electrons. So where are the other 4? The answer to that is that they are up here in 2 lone pairs. So up at the top of the A, they are up here as 2 lone pairs. So it cannot be linear like it was up here. The A up here had no lone pairs, but the A here does have lone pairs, and they push down the bond pairs like that. They skew the bond angle. That would look like this. So here is a central atom, this purple one, and here are the 2 atoms attached. But instead of being in a straight line like they were in the linear molecule, the 2 lone pairs up here on top of the central atom have pushed down the 2, they've repelled the 2 bond pairs. So 2 silver or gray bonds here, the lone pairs have pushed the lone pairs have pushed the bond pairs down in angle. So again, remember what a tetrahedral was. A tetrahedral's bond angle was 109.5. A lone pair from that takes away 2.5. And for each lone pair, we're going to take away 2.5. If we take that away, we'll get a bond angle of 104.5. Again, those bond angles are important, so you should make a note of them, and you should try and learn them. The shape of this molecule, or the name of this molecule, is called a V-shaped molecule. It's V-shaped because of this. It's V. It's in a V. Some people call it a bent molecule. That's okay as well. V-shaped or bent. So those are your 5 different shapes of molecules. Let's quickly recap them. There's 2 AX2s, and it depends on the central atom. If the central atom A is in group 2, it will be linear with a bond angle of 180. If the A is in group 6, then it will be V-shaped with a bond angle of 104.5. This is due to the lone pairs on the central atom. There are 2 cases for AX3. AX3 where A is in group 3 with 3 valence electrons. This is trigonal planar, flat on your hand. Okay, the central atom, no lone pairs, just 3 bond pairs equally spread. If we have AX3 where the central atom is in group 5, like nitrogen or phosphorus, then we're going to have a bond angle of 107, and it's going to be a pyramidal shape. Why is this the case? Well, the lone pair on top pushes down the bond pairs. It repels the bond pairs more than they repel each other, and it pushes them down and decreases the bond angle and knocks them out of being a flat trigonal planar molecule. The last shape then is the AX4 general formula, where A is in group 4, and it's covalently bonded to 4 surrounding atoms, and they're all bond pairs. In this case, they will spread out equally in 3D space, a bond angle of 109.5. We call this a tetrahedral. Let's apply this to real life molecules now, guys, and then that will hopefully help you guys to learn the different shapes. So what we're going to do is I'm going to get you to go ahead and fill out this table. I'll show you how to do the first one. I'll do the first one with you. Let's look at this molecule BCl3, where B is the central atom because there are less of them. So there's 1 B and 3 Cl, so B has to be in the middle. So the first thing you've got to answer here is you figure out the number of valence electrons around the central atom. B is in group 3, so it's got 3 valence electrons. 3. How many bond pairs does it have? Well, B is bonded to 3 chlorines. So if B is bonded to 3 chlorines and it only had 3 valence electrons, well, they're going to make 3 pairs, 3 bond pairs. So we'll have 3 bond pairs, and there's none left over, no valence electrons left over to make a lone pair, so 0. Diagram wise, if we were to draw that, we would draw the B in the middle and the 3 chlorines around like this. There's 1, there's the second, and there's the third, BCl3. The name of that shape is trigonal planar, no lone pairs. Bond angle 120 degrees. Right, so your turn to finish off the rest of these, and we'll see you. We're going to correct them in class the next day.